Thank you, Craig, and thank you very much to Alex and organizers for inviting me. I'm very pleased to be speaking here. I realized that one of the major points of this workshop was to generate discussion and to have people think about open problems. And is that are you asking a question? And I think from what I've seen, that it's been very successful in generating a lot of discussion and people working together, and open problem session and all of that. And I can personally say that from my talk on Monday, I have already gotten several different people answering questions that I posed and proposing family number fields that are interesting and things like that. So I think this workshop has been very successful so far. And so then I was kind of reminded by Alex right before this talk to think about continuing this spirit in my talk. So I'd like to try to ask some questions and get some discussion going in my talk this time too. So don't let me forget that. So I'm going to talk about parameters for homomorphic encryption. This is joint work with Kim Line, who is a Finnish PhD student at University of California, Berkeley, who is working with Ken Ribbett, and he's been working with me off and on over the last few years. He's about to start a postdoc with my study. So what I'd like to do, this talk will be kind of a combination of, when I came to the crypto day at Irvine in the spring, I actually gave two talks. One was kind of a big, like, colloquium style kind of advertisement for homomorphic encryption. What is homomorphic encryption? Why is it interesting? What do we do with it? And then the other was the title of, supposedly, the title of this talk, which was Attacks on LWE. So this talk that I'm giving today, you could think of as kind of a combination of those two talks, which is I'd like to still kind of remind you of the importance of homomorphic encryption and why we're so interested in what it can do, but also to give you a lot more specifics on the constructions and how do we set the parameters, and the way that we set the parameters is directly related to what kind of attacks do we know, and how good can we make these attacks, and where is there room for improvement on these attacks, which will then affect our parameters and our performance for our homomorphic encryption scheme. So that's, and at the end, if I have time, I'll tell you a little bit about very practical aspects of what we're deploying. Okay, so homomorphic encryption, I know it's been mentioned by a number of people in this workshop. The idea is just as the name says, homomorphic encryption is a way to encrypt so that things stay kind of homomorphic in the sense that you can take ciphertexts and you can add them or multiply them, and those the outcome is the same as what you would have gotten if you had encrypted the inputs after having done those operations. So I sometimes like to draw a nice commutative diagram that says that homomorphic encryption means you can encrypt and then operate, or you can operate and then encrypt. And then the outcome that you get will decrypt to the same values. So the important part, and the reason there's quite a lot of confusion around nomenclature in this area, right? So fully homomorphic encryption is the term that was used essentially when Craig first came up with the solution in 2009 to refer to the fact that it's encryption that does both operations, both addition and multiplication, as opposed to something like just one operation, which you could do with RSA or Caillet encryption. So if you see fully, in other words, FHE, if you see fully homomorphic encryption, it's usually referring to the fact that you have both operations are possible on the ciphertext. And the important thing here is you might say, well, fully, in what sense is that fully? That's only addition and multiplication. What about division and things like that? But really, when you think about it, what this translates into is this means that you can do any circuit. So when you're working on a computer and you're having the computer doing all kinds of arithmetic, including things like division or comparison or all types of operations, really a computer is implementing all of these things just as circuits. And it may be that it has to do things approximately, or it may be that it's a very, very deep circuit. do what we think of as simple arithmetic, like simple multiplication or division, but really this is fully homomorphic encryption in the sense that it can do any circuit. So I think one of the issues, the kind of second issue of the nomenclature, I'll just mention it here, you'll see it later in my terminology, is that after the FHE, the fully homomorphic, was kind of fairly well accepted, then everybody started talking about PHE, SHE, so P was partially homomorphic encryption, S was somewhat homomorphic encryption, and then we got to something that was supposed to be more precise, which was leveled homomorphic encryption. And so now you'll see later my personal preference is just to use practical homomorphic encryption. So what do we mean by all this? Somewhat, partially, leveled, practical, all of these things. So if we depart from the land of fully homomorphic encryption, so fully means any circuit. So you set up a system, and then no matter what circuit somebody comes along with, you can do your encryption, and your system will work. So somewhat doesn't mean that it's not homomorphic. It's still homomorphic, but the depth of the circuit is limited. That is, you cannot do any circuit. You say ahead of time, you say, hey, it's like sticking up a flag that says advertisement. I can do this amount of homomorphic computation, so don't give me any circuits that are any deeper than this. So it doesn't mean that it's only partly homomorphic. It's still homomorphic. It's just the depth of the circuit is limited. So the nice thing, since Craig's solution in 2009, we've had kind of a flood of papers producing solutions, constructions for homomorphic encryption. And they've, to a large extent, been based on lattice-based cryptography. So as you could see, for example, in Mariana's talk this morning, where she's talking about the approximate GCD problem, you might say, oh, well, that's not lattice-based cryptography. But it's very, very related to lattice-based cryptography in terms of the best-known attacks and stuff, too. So this is just kind of a representation of what homomorphic encryption solutions look like in lattice-based cryptography. So the idea is that messages are encoded as lattice points, and then they're encrypted by adding some small kind of displacement or error. So the noise is used in the encryption, and each fresh ciphertext has some initial noise. And then as you do operations, the noise grows. So with homomorphic addition, the noise is roughly just the max of the two input noises. So it's not bad at all the way the noise grows. But unfortunately, one of the things that so many of the schemes and the improvements over the last 5 years have been aimed at is handling this problem, which is that as you do multiplications, which corresponds to the kind of the depth of the circuit you're trying to evaluate, as you do more and more multiplication, this noise increases multiplicatively, and it becomes very hard to handle. So why hard to handle? What does that mean? What's wrong with having the noise grow? Well, so here's kind of a picture of what it means to do encryption. If you think of having messages that you're encoding as lattice points and then kind of encrypting with a bit of error, so here's two encryptions, and then when you add them or multiply them together, as you could see, kind of the magnitude of these red arrows is growing. And your ability to kind of decrypt is based on using the secret, being able to kind of remove this error. And kind of you could kind of see from the picture here that what happens when your error gets too big is that you will decrypt incorrectly. You will decrypt to the wrong thing. So that's why you need to make sure to keep the error small when doing homomorphic operations. So the basic blueprint, which we all attribute to Craig's initial solution, is this bootstrapping theorem in this area, which kind of allows you, when the error grows too big, if you have the ability to kind of homomorphically decrypt the ciphertext, so kind of that's why it's called bootstrapping, is kind of inside the encryption circuit, you're able to actually homomorphically decrypt the ciphertext, then you can kind of refresh the noise. So this is kind of the blueprint or the basic idea behind fully homomorphic, meaning you'll always be able to continue doing more and more operations, a deeper and deeper circuit, because if your error gets too big, then you'll just do this kind of bootstrapping operation to kind of crank back the error to a smaller size and then keep going. So that's kind of the basic idea. Unfortunately, so this kind of bootstrapping can be fairly expensive, although we have seen some recent papers this year where picking parameters carefully, you're able to do bootstrapping very efficiently. But for typical applications, the bootstrapping operation is pretty expensive. So there are a couple main things that we did back in around 2011 when we had the first really practical homomorphic encryption schemes based on RLWE were proposed by Brakersky-Vaikunathan and Brakersky-Gentry-Vaikunathan. So the main thing that we did and that we continue to do has to do, these are kind of practical improvements that have to do with how do you encode the data so that you can kind of squash your circuits. You make the circuits that you want to do for basic arithmetic and really practical tasks. You make these circuits very, very shallow. And shallow circuits are very, very easy to implement with homomorphic encryption, especially if you forget about bootstrapping. So if you do remember I told you I prefer the term practical homomorphic encryption. If you don't like practical, you could put somewhat or partially or leveled or whatever you want as this term right here. But the point here is that you can only do a predetermined depth. So this is very reasonable for applications. You're a cloud service, you're going to provide some service, you're going to evaluate some predictive function, for example, for medical purposes or whatever. You know what the function is in advance. And you can describe that in terms of as polynomials or as a circuit, however you want to describe it, but you know what the depth is. So when you deploy your system, you say, this is the depth of the circuit that I can handle, and here's what we're going to do. So practical homomorphic encryption is practical in that sense, and it makes perfect sense for applications. And of course, it requires that you actually select the parameters based on the function that you need to compute. So I'll talk more about the details of that in the end. Okay, so we've already talked, a number of different talks have mentioned both learning with errors and ring learning with errors, introduced respectively by Regev and Lubashevsky, Pikert, and Regev. And they're closely related to lattice problems in the sense that there's these security reductions between these problems and hard lattice problems. And just to remind you, the notation that we're going to use for this talk is pretty similar to what I also used last time. So Q is, in everything that I always work on, Q is always an odd prime. As I said last time, some people do not make the assumption even that it's prime. It could just be an integer modulus. These AI and S are going to be vectors with coefficients mod Q. So AI are these kind of random vectors. S is a secret vector. And the EJs are going to be the error values, which are also small. And so just as a reminder of what the learning with errors problem is, it's the problem of given a bunch of samples, kind of A is our randomly or vectors generated uniformly at random, and given a bunch of kind of approximate inner products with a secret, can you recover the secret? Each one of these lines is a separate sample, and what it does is it takes this random vector A, takes the inner product with S, adds some error E sub I, and outputs B, and these given a collection of these samples, the search problem is to find the secret, and the decision problem would be to just decide whether these are LWE samples or not. And the same basically goes for our LWE, except for the context is that the vectors can now be viewed as coefficients of a polynomial, and the multiplication in the polynomial ring makes a lot of things a lot easier. So, and the sampling thing is. And so
just a note that from our LWE samples, you can also create LWE samples just by looking coefficient-wise in your polynomials. So the typical error distribution that we always talk about is this Gaussian error distribution. So you should think about this being happening kind of in continuous land, where you think of your Gaussian error distribution being in Rn or in Cn, but then in practice, to do all of these things mod Q, as I kind of went into in great detail on Monday, you have to kind of discretize these errors and think about what it means to do this Gaussian error, discretized Gaussian error distributions mod Q. So the one thing that I really didn't talk about on Monday, and that I wanted to make sure to talk about a little bit here, is so what are the actual homomorphic encryption schemes? So the BV scheme, Brajkowski-Vikatunnathan, it was kind of a basic starting point, and along with the improvements from the Brajkowski-Gentry-Vikatunnathan, essentially this crypto system still is one of the main ones that's used for applications. So if you look at the IBM homomorphic encryption library, which is publicly available, I think it's called HElib, either that or FHElib. HElib, right? HElib, yeah. It's based on essentially on the BGV scheme. So I thought it would be worth kind of saying in a little bit more detail exactly how this homomorphic encryption scheme works. So you have, as I said, your modulus, and you have your dimension of your lattice, which is, you can think of it as the number of entries in your vector, or you can also think of it as this, the degree of this polynomial ring that you are, the degree of the monic irreducible polynomial that you use to form this number ring here. So Q and N are very important in terms of the security, selecting Q and N properly, and we'll see that when I talk a little bit more about the attacks. And in our case, in our implementation, we always use only 2-power cyclotomic fields. So for us, N is always a power of 2. In general, if you use general cyclotomic rings, you can use, N could be arbitrary. It would not have to be a power of 2, but there are different security considerations that you have to think about there. And hopefully I convinced you all in my talk on Monday that you probably should just not even think about using any other rings for this. There are probably some that are suitable, but if you want to do that, then you should be very careful and construct them very precisely yourself. The encryption, this is something that confused me when I first started working in this space. What do you mean by plain text space? So I think part of the reason that that's confusing is there's a lot of different ways to encode data. So just think about this whole problem space. I'll give you some applications in a little bit having to do with, you know, genomic computation or machine learning or predictive analysis or whatever it is. There's a lot of different tasks, and for each of these tasks, the data comes in different forms, right? You could be talking about floating point data, which is like measurements of tumors. You could be talking about bits that has to do with like evaluating, you know, decision trees for machine learning, like Bayesian analysis, like trying to help you decide which, you know, route to take if you're driving to work, and, you know, looking at traffic flows. Or, I mean, the data can come in so many different kinds of forms. And yet here, you know, if you look at our setup here, we're talking about a very specific kind of format for our data. So this is often called like the ciphertext space, in the sense that once we get the data into this form, the claim or the promise of homomorphic encryption is that it allows you to operate on data in this form. That is, as if you multiply ciphertexts or if you add ciphertext, you get the same thing that you would have if you had operated on that data in this form. But so this is kind of before, the plaintext space is kind of before you get to this point. So in other words, it's how do you take real data and then kind of smush it into this ring And this also has to be done homomorphically. Otherwise, the whole thing won't be homomorphic in the end, even though the ciphertext space is allowing you to operate homomorphically. The plain text space also has to be kind of embedded in this ciphertext space in some kind of homomorphic way. And the thing that I found very, very confusing as a mathematician is I'll take this other number, t. So at first, the first iterations of this, t was always equal to 2. And if you remember, I said that q was typically an odd prime. So we take a space rq, and then we take it mod t. So what does that look like to you? That looks like the trivial element. Everything's gone, right? It just makes no sense whatsoever. So this is a very, very important point, I think, from the mathematical point of view, is that everything has to be done extremely carefully. If what you're going to do is you're going to have a plain text space that's mod t, you're going to have a ciphertext space that's mod q, how does that even make sense? What's going on? So it turns out, I mean, I was just enraged when I first saw this. I'm like, what are you talking about? You're going to do this mod q, and then you're going to do it mod t. And q and t are co-prime. So what do you have left? So the point is that you actually, it's kind of surprising, but you actually can do this, but you just have to be very, very careful. And that's why I kind of made a very big deal last time about where the error lives, and that you take it and you put it, instead of equivalence classes mod q being between 0 and q, you put it between minus q over 2 and q over 2, and you really think of these as small numbers. All of that really matters for making encryption and decryption work properly. Question? Okay. Yeah. So let me just say specifically again what this is. So in the encryption process, when you're encrypting something, you have a secret S. You're going to generate random values A, which are your kind of auxiliary randomness in your encryption. You're also going to generate your error. And so when an attack, not in this description right now. Yeah. So then an attacker is just going to see a bunch of samples like this. And an attacker doesn't know what S is nor what the error is. But these things, they are public, the Q and the T and the N. Oh, this was supposed to be, sorry, this was the Gaussian distribution. So it just means that the error was sampled from this Gaussian distribution. And when we're doing polynomials, this means kind of what I was describing last time, which is this spherical Gaussian error, but it's kind of discretized. So error is chosen component-wise in the polynomial ring, having already specified a basis in the polynomial. Okay, so when you have ciphertext, if you have a ciphertext and you actually have S, then what you can do is you can decrypt by taking your B, and there you do have S, so there you can subtract off your A times S. And then what you do is you do this mod T to kind of get rid of this error. So again, for the mathematicians in the room, how does this make sense? Well, this is one way I like to think about this is doing things mod Q. Think of Q as like a very, very large modulus, which in practice it is actually. You know, not as large as RSA, but something like 2 to the 128, something like very, very big. And one way that I like to think about it is really just as a kind of the size of a ball that you're operating in. You really like to think of your lattice as just being like a Z lattice. Like there is no modulus in some sense, but it's just to make everything finite so that you can actually stick values into a computer. And so that's one way in which you can kind of think of it as making sense, is you really try, what you have to do is keep track of which things can wrap around modulo Q and which things cannot. And so one thing that's very important is with this message space and this T times the error, none of this stuff is allowed to wrap around modulo Q. So everything that you do, multiplication and addition and everything of messages and and this error stuff, all of this has to always stay below Q. Then it will make sense. So this stuff can wrap around modulo Q, but this stuff cannot. So. What did you mean by cyclic ring? In the ciphertext space or the? No, it actually happens mod Q, but then in the end, when you decrypt, it will happen mod T. You will decrypt mod T. Okay, so actually, you know what? It's too bad I didn't. I should have written out the whole multiplication and addition, but it's just multiplication and addition in these polynomial rings. So there's another important point that you have to make sure of, which is that for us, we use this cyclotomic polynomial where n is the power of 2, so it's particularly easy. It's just x to the n plus 1. But you also have to make sure that your computations don't wrap around mod n. So you're going to take, it's like you're taking equivalents, your representatives of equivalence classes of these polynomials. So this thing here, I don't know if that's what you meant by the cyclic ring, but this is just in this thing I called RQ, which is z mod q z adjoin x modulo x to the n plus 1. So these are just polynomials. So it's ciphertext, it happens in those rings. But then in order to make it come out properly in the end, you just have to make sure that you impose certain rules on what you're going to do. Otherwise, you'll just get a bunch of garbage and it won't make sense. Did that answer the question? I'm not sure. Okay. Yeah. So the one thing I'm not talking about here is what you would do if you were in LWE land, so without the ring structure. And there are ways that you can make it work with even a little bit more bookkeeping. But everything that we do is kind of more efficient in our LWE land if you use the ring structure. So as long as we don't break these assumptions for cyclotomic rings, we're going to stay in our LWE land, not in okay, so I said I would at least give a little bit of a mention of some of the applications. So these are things that we've actually done, which is kind of fun because it's fun to be able to show people in other fields, you know, like researchers in bioinformatics or doctors or things like that, these kinds of applications. So one of the first demos that we did, this is a paper that appeared in the Journal of Bioinformatics, Private Predictive Analysis on Encrypted Medical Data. So we just took like a sample medical prediction task, like predicting your likelihood of having a heart attack or predicting your likelihood of having diabetes or something. So this is based on some very simple health data, but that's data that you might want to keep private. And it uses, in the case of heart attacks, there's been lots of work that's public domain over decades, which you may have heard of the Framingham Heart Study, which developed models for predicting a patient's likelihood of having a heart attack. So in this case, these models are not private. This is not something that Microsoft spent a lot of money to develop these models, and we don't want to share the model. In this case, it's an example where the model itself is public. You can go online right now and look up a function which tells you your likelihood of having a heart attack. The only problem is that most people are not really tech savvy enough to do that and then to want to implement the function themselves and things like that. So imagine you had a cloud service where someone could, on their own laptop, they could type in their private health data. It would get encrypted on their laptop. It gets sent up to the cloud. The cloud does this homomorphic computation on their encrypted data and sends back an encrypted prediction to their laptop. And so and then they can decrypt it locally, and then they can get their likelihood of having a heart attack. Or the point is that there could be other private models. Microsoft could have, not just Microsoft, but any other company could want to deploy a service where they had some private model that they didn't want to share with their clients. And the client could do this kind of computation as well. And I mean, just so you get an idea of how practical practical homomorphic encryption is. So we showed this demo. It's online. You can actually see a link. I showed it 2 years ago at a AAAS meeting at a newsroom in front of reporters. So I was glad it worked and didn't fail on me. But doing the homomorphic computation on the encrypted data took 0.2 seconds. So here's everybody thinking homomorphic encryption is not at all practical, and I type in my data and I send it up to the cloud, and before they can really blink, I have my answer back already decrypted on my laptop in front of me, and showing on the screen. So that kind of helped to get the idea across that if you do limit to a certain kind of finite, concrete, small amount of computation, these things are extremely practical. So in this case, we were taking logistic regression function. We were approximating it with polynomials. The degree of the polynomials was something like around 8. So that's what we call level 3, because if you have to evaluate a polynomial of degree 8, you can do that in a circuit of depth 3. You just take 2 and you square it and you square it again, and you get degree 8. So this is essentially level 3 homomorphic encryption that we use to do this, which is very, very shallow. We can do things that are small level like that very, very efficiently. I'll just give you the other extremes. So also, I think in 2013, there was the crypto paper that did homomorphic evaluation of AES. The authors, I should have written them down here, were smart. Somebody else, maybe? Yes, thank you. Smart Gentry Halevi, thank you. So the AES, to evaluate AES, government standardized block cipher homomorphically is a very, very, very deep circuit. And if I remember correctly, the number of levels you needed was in the 30s at least, something like that. So that looked at that same time a lot less practical. These days, even improvements have been made in that setting as well. But so anyway, if you stick to very small levels, things look a lot more practical. So one of the ongoing projects we have right now, which is pretty fun and interesting, is that how many of you have heard the buzzword deep learning? Like you see it like even on magazine covers these days. Deep learning, right? So deep learning is this idea of taking, machine learning, this concept of neural nets, like the brain. How does the brain learn? For a long time, decades, it's been known in machine learning that you have these things that we call neural nets to evaluate, to kind of build models for learning. So deep learning means taking neural nets and kind of looking at successive levels of these neural nets. So think of my heart attack prediction as being one level. It's like a very simple model. It's like a logistic regression. And the thing they call, there's this thing they call an activation function, which is usually a sigmoid. And that's the thing that's kind of challenging to evaluate. So what we're doing in this CryptoNets project is doing quote unquote deep learning, which means doing successive levels of these neural nets, which you might think, oh, that sounds horrible. You had level 3 already for one, and then you're going to compose it with itself again and again. It looks like the degree of these things would just blow up exponentially. And you're right. And so that's why the funny thing about deep learning is by deep, they typically mean like 6 iterations, which to me doesn't sound that deep. But what we can actually do is we can get away with approximating deep learning by many copies of shallow learning. So we can kind of get away with doing like 2 or 3 stages of this, essentially the computations that's on the order of our heart attack computation. So basically by working with machine learning researchers and trying to figure out how to best approximate some of these deep learning tasks with things that are more reasonable and tractable for homomorphic encryption, in joint work with a bunch of people at Microsoft Research, we're actually able to evaluate these crypto nets homomorphically, which is an example of deep learning done on homomorphic data. In this case, the training, that's absolutely right. So we separate training and classification from machine learning tasks. So all we're doing in this project is classification, because that's hard enough. However, we did have some other work. I might even, nope, I don't have the slide about that. Sorry. We did do some other work where we took simple machine learning models. So we took linear means classifier, which is really simple because it's just linear functions. And we took Fisher's linear discriminant model, which is much more complicated. And we actually did training on those. But there we assumed that we had labeled data to train from where the label was in the clear. So the data itself was encrypted, but the label was unencrypted. So supervised learning in this setting where you wouldn't mind having the label being transparent. This was the picture of the kind of the successive levels of the nets, and you can see we're only doing like 3 levels now. And so another application that we've done is predictions on genomic data, which is pretty fun too, because genomic data is something that's really interesting to think about how to protect going into the future. Okay, so now let's get to the question about what was the title of my talk, which had to do with attacking LWE. And the reason that that's important is to figure out how should we set these parameters for homomorphic encryption. So by setting parameters, I mean choosing N and Q primarily, NQ and sigma, where sigma is the width of the error distribution. I mentioned briefly on Monday as well, and other people have talked about this here too, that very roughly there are these security reductions which are due to Regeff and then Pikert and Lubitschek, Pikert and Regeff, which relate the hardness of these LWE and RLWE problems to other hard lattice problems. So for example, if gap SVP sub gamma of n means that's the problem where you try to say whether the shortest vector in a lattice is longer than a given gap, gamma. So their theorem was that for a certain error distribution, if gap SVP for this gamma, n times q over sigma is easy, then LWE is easy. So there's a whole zoo of security reductions like this, and a similar one for our LWE, but which is complicated and actually requires a quantum reduction. So this is kind of the starting point, and then I take I'll just be totally upfront. I take completely the opposite point of view. So I just say, okay, let's ignore the security reductions. Say we believe that some people have proved some security reductions, so they think that these problems are hard. But let's just see if we want to directly attack these problems with the tools that we have. How fast do our attacks run? What can we attack in a reasonable amount of time? And so there's some kind of standard or fairly well-known approaches to LWE and thus RLWE. And these are primarily attributed to, so the main 2 references that I'll give are Michiancio and Regeff, who provided a kind of a distinguishing attack by it requires finding a short vector in a lattice and using that to distinguish LWE samples from non-LWE samples. And then the Lintner-Pikert decoding attack, which actually finds the secret given a bunch of samples, also by doing kind of lattice reduction. So that's a kind of starting point for our work here. So the question is, if you look and see, even if you look at this reduction though, you can see that as the gap gets bigger, the problem gets easier in a sense. So I think this is a good time to pause and just state the obvious. This is something that I think probably everyone in this room knows, but it's somehow not always completely apparent, is that when we talk about shortest vector problems, we have if you think back to the whole zoo of problems that Daniele showed in his slide on the first day, these hardness results are very, very, very dependent on what the parameters are. So if you think about shortest vector problem or approximate shortest vector problem, can I find the shortest vector in the lattice? LLL is an almost 30-year-old, very well-known algorithm which runs in polynomial time for finding an approximate shortest vector. But the problem is the approximation is rather bad in the sense of being exponential. So the gamma, or this thing up here, the gamma is very large. So as long as your gamma, your approximation factor, is large, the problem is easy. So that's the kind of stating the obvious that I wanted to say here, is that with LLL, we can find short vectors where short means, well, not that short, but precisely how short it is a very, very interesting question. So what the basic idea is that with using LLL, if Q is large enough so that essentially this security function kind of doesn't tell you, it says that I mean, it's kind of vacuous when this value is large enough, right? That you say that if it's if gap SVP is easy, then LWE is easy. Well, yeah, if you make this gamma large enough, then gap SVP is easy. So is SVP, or approximate SVP. So what we showed is concretely any instance of LWE where Q is this large can be broken in polynomial time using 2n samples. And in practice, you can do significantly better than this. This is just kind of what the theory tells you. So I want to talk a little bit more detail because it really matters when you're trying to set parameters. What does this mean? So so Kim did a huge amount of work. I mean, this is just a representative sample of attacks that he ran, but he ran hundreds, actually thousands of successful attacks on LWE instances. But so just to give you a sense of what this attack data means. So if you think of n, so n is the dimension of the lattice here. And to be honest, like for homomorphic encryption, we never even deal with an n smaller than 1024. Like 1024 is kind of like a minimum size for that. And then there are other applications of lattice stuff where for like signatures or something, the n could be smaller. But and then this is the number of samples, and then this is the size of Q. So how big is Q? And again, like I said, compared to RSA moduli, these are very small Q, right? 2 to the 50, compared to like 2 to the 16,000 or something like that. But when you think of lattice problems, if you go all the way back up here, so if you look at problems like, you look at the challenges, I think I remember from Tice's talk. So if you're using like the sieving algorithms, or maybe it was pruning in enumeration, or I can't remember what, like the biggest challenge that's been solved is 116, is that right? Or is it, you're still working on that one? 107. 146 has been solved? Oh, with other one. Okay, good. So maybe that was used. So, these are math, and can you give us an idea of like the compute power for solving a challenge like that? Yeah, or months, years of computer time, something like that. Yeah. So these are attacks which are, this ran in like 24 minutes. And then if you see what the Q is size, 2 to the 19. And then as you get already lattice problems with size dimension 350, that's a pretty considerable size, shortest vector problem. And so what we're able to do is we're able to run these attacks very, very efficiently. And what it does is it gives us kind of some side channel information about how well these lattice algorithms are actually working. That's kind of interesting. So one reason I like to focus on this attack data, I'll show you a picture of it too, is that I think it's a very, very efficient way. It's kind of like the opposite of what you think you would do. It's instead of trying to solve SVP so that you can see how hard LWE is, you solve LWE so that you can see how good your SVP algorithm is. That's kind of a reverse of the usual. So for example, for a lattice of dimension 350, we're able to solve a LWE challenge using around 800 samples in 3.7 days. Okay, so actually, I will come back to this in just a second what the method is. But so first, let me just show you this data since I just showed you that graph. Yeah, there is. Yeah, but it's funny. Okay, so that's a very good point. I'm glad you brought that up. One of the funny things is that in practice, a lot of the people that have implemented these things, and even Piker's table in the Lindner Piker's table in their paper, they fix sigma. And so one thing we start, and also in applications, including like the TLS implementation and all these things, they just kind of fix sigma. And so actually I was talking with Daniele Miciancio about this, and of course that really doesn't make any sense, right? Like from some kind of theoretical point of view, if you fix sigma, then there's always going to be kind of a polynomial time algorithm. But for crypto, the only thing that matters is the time, you know, how long does it actually take to implement these attacks? So so here, Daniele, I'm paraphrasing here. Daniele's argument is that if you take, if you kind of go back to the Schnorr construction and you look at there's a parameterization of increasing block size that you can do to get, you know, better and better approximation, and that if you look at that parameterization, strictly speaking, you can claim that these algorithms are polynomial time even as the block size increases. Polynomial time. Maybe we can talk in more detail offline. You probably know more about it than I do. So I think one interesting thing in practice would be to see, like, if you look at that approach, whether that gives you anything better than, for example, this approach. But yeah, that's another point. So it is true that in both in applications and in attacks, what we're typically doing is fixing this sigma. However, that for these attacks, you can let sigma grow, and that'll just, you know, change the way that n equals to. You can see it in the estimates how it grows with sigma. Okay, so the reason I want to show this picture is this should be compared with the table that I just showed. So what this is doing is it's saying, okay, so let's look at all of these different LWE problems for these varying dimensions from 75 up to 350. And then let's look at, on this axis, this is essentially the approximation. It's telling you the constant in the approximation factor in LLL. So this is kind of important. This is like the key quantity that I would want you to remember from this talk, is that LLL finds, okay, so I'll just say it finds V, which has length, the length of V. Okay, so in a lattice L, L has the dimension of L is n, and the length of V is less than or equal to 2 to the, I'm going to write mu times n over 2 times the length of the shortest vector. So this is what LLL gives you, is that for a lattice L of dimension n, it finds a vector V, which is no longer than the shortest vector times an approximation factor. This is the thing we're calling gamma, where this approximation factor is no worse than 2 to the n over 2. That's what the theorem gives you the guarantee of. But there's a potential that it's giving you something much better. And this mu is measuring how much better potentially is this approximation factor. And just for completeness, I'll write down the running time is roughly n to the fourth log 2 squared. So this gamma, the thing that it is kind of counterintuitive from a theory point of view is that really the thing that matters the most is what is this mu? How good is this constant? That's what you need to know in order to set parameters. So if you look at what this graph is doing, this graph is showing you kind of how mu grows as the dimension grows. And here's my open question that I want to ask the audience. And I'm not sure if anyone other than Hendrik will have had any part in the discussions that have taken place over the decades on this topic. But so if you look at this, let me tell you what the red and green dots are. But you see a pretty kind of convincing pattern here, right? So the red dots means we generated some LWE samples, and then we tried to attack using LLL, and our attack failed. So these red dots are they fail. The green dots mean we succeeded. So, but why are they plotted, like what's this axis here for? What this kind of means is that before we ran the attack, we knew that if this approximation factor mu was this good, then the attack would succeed. So everywhere where you see green dots and you kind of see this growing like this, that is kind of showing you that this mu was roughly of that size. And especially when you have it very close to the red dots. The red dots don't really mean anything because our attack could fail for some weird probabilistic reasons. So sometimes you'll get, a red dot above a green dot, which is a little confusing, but I think it's just this kind of probabilistic nature. But overall, what this is doing is this is showing that this is how we can expect this mu to grow over time. So here's my question. I have seen and heard in the literature some people posit the idea that this function, this mu, how well LLL behaves as the dimension goes up, that this mu could actually start decreasing at some point. And so this makes no sense based on our experimental data. Yes, that's right. And I should point out, so another thing I should point out is that this is a particular lattice. I mean, the lattice that we're running this on looks like this. So it is kind of a special lattice. I'll go back to that in a minute. But the point is that it doesn't look like it's going to start decreasing. But I've heard that conjectured. And if it did start decreasing, that would be horrible for lattice-based crypto. Right? So I heard your comment. So what, like this is a very kind of simple description of this mu. But you can take this and you can, the way that Fong and other people usually write it, you just turn this into the thing that they call the, whatever it's called, root Hermite factor, whatever, which is like some other function of this thing. And what they're basically saying is that, I think they're essentially saying it approaches a constant. So like if you look at this, like this looks like it could have an asymptote here. And that's the question is, so is this function, is it logarithmic? Does it keep going? Does it go to a constant or does it go? Yeah, but using a simulation or using actual? Yeah, but then what was the biggest dimension that you went to? Like 200, 100? No, but I'm saying as it grows. There's simulations that certainly, show this, that they think that's what happens, but not by running actual solvers. I'm not. I'm posing a question as to the behavior of this mu. And this is, I mean, one of the most recent papers is the Fong Mugen, I forgot the other co-author, from ants, it's called, approximate LLL revisited or something like that. But I mean, we also have, like, people in my group have run these simulators for larger and larger n as well, but they're just simulators. They're not actually solving lattice problems. They're just simulating the running time if the lattice problem were being solved. And we don't know how accurate those simulators are. So I think the point I'm trying to make here is this is a way around. So why is it hard to estimate mu? Like, say you want to get a value for mu when n is 1,000. That's very hard to do because you can run LLL and you can get this, but you don't know what this is. So you can't figure out mu from that. So what I'm saying is this is a way of kind of getting side channel information about what mu is in the case that we did not find the shortest vector in these lattices. But we found a vector which we knew was at least short enough to solve our LWE challenge. And it had to be at least as short as something like this. And so that's how we know what the mu was. We know that our using like Minkowski or something like that. I mean, yeah. So, but that doesn't mean you know what it is. You have an upper bound on it. I'm saying it matters what. I mean, we're not using, first of all, we're not using random lattices for crypto. We're using, I didn't show you the format very precisely yet, but for LWE samples, this is the lattice that we have to find the short vector in. And this is, the performance that we find. And I still think it's an interesting question. How does mu grow? And we have these simulators that give you an idea how we think it grows. But like I said, I still think it's open whether mu can actually start decreasing. I've seen a suggestion that could happen. I've seen no evidence that it happens. I just think it's very interesting. Because if it is possible, then that will be very, very bad for our crypto environment. Are you talking about like the fact that like this? Yeah, I think that would be deceptive. But like I said, we don't know. I mean, it's like to run even more. To us, it kind of looks like it's not hunting down, but that's the question. I mean, the suggestion that I've seen is that it kind of looks like this. Has anyone else heard or seen that suggestion from the last few decades? Okay, so let me see. I have already taken up an hour of time with all of these discussion, and well, that's good because we wanted to have some discussion. So at this point, I can stop, or I can also say more about the actual, this is the practical implementation of crypto and the kind of encoding and the parameter selection that we get from doing these lattice estimates. But in terms of the mathematics, besides the interesting mathematics that goes into kind of encoding data, I think this was kind of the key point from my lecture that I wanted to get across. So I think maybe this is a good point to end on.
Yeah, so that's a very good point. So when you talk about the cost, you should really include like not just the depth of the circuit, like also the number of additions and things like that. They do contribute to error growth, so you should actually be careful about error growth that comes. But when we say depth, we just refer to the multiplication. Oh, that's a very good question. So we actually did a kind of a new approach in this new implementation that I had in the end of my slides here, where we do an error simulation. So yes, I mean the ciphertext, like what we'll do is instead of actually operating on the ciphertext, we'll just do a kind of simulation of what will happen to the error as we operate. And there it does. It kind of carries in there the amount of error, and we can kind of see how it grows, and then we can use that to back up and set the parameters that way. Because that simulation is a lot more accurate than if you just take the upper bounds. Like if we take the upper bounds every time on the errors and the error growth, the upper bounds are pretty bad, and it means we'll set parameters conservatively, which is good because you won't end up failing by incorrectly decrypting. But it also means that your system will be a lot less efficient than it could be if you actually